Okay, we are on the air. I got requested twice for this, or at least twice, maybe thrice. Carpool. And it's car just pulled in. It's unfortunate because one of the people who was asked about it's not here. And with all the shenanigans going on a couple blocks away, who knows? So, the question was, what's the difference between a CMOS and a CCD image sensor? So, charge coupled device versus complementary metal oxide, semiconductor. So I'm going to do some history and some light physics on these. It'll be very light physics. So back in forever ago, when we were first figuring out silicon junctions and PN junctions, we talked about this a little bit before. If you got a diode, you've got a P region and an N region. And this is doped with an excess of electrons for its majority carrier. And this side, the P side, is doped such that it's got an excess of holes in its majority carrier. So it's not actually welded like this. What you do is you take your silicon and you mask one side and you hit it with an electron gun or chemical vapor deposition, and then you mask the other side and do that. And if you look at this from the side, so it's much thinner, right? If you think of a wafer, this dopant only maybe goes, and that's an exaggeration, it's only microns down into it, depending on the device. So, what happens is you get some electrons that come this way, and you get some holes that make that way, and they make what's called a diffusion region here. It's kind of neutral, and how heavily you dope this, it gets into differential equations about how wide that is and carrier lifetimes and whatever else. So thermally, what happens is, electron. If I excite my atom enough, the electrons in it, they'll pop off from what I guess it's called the valence band into the conduction band and start being a conductor. And I'm not going to go into band diagrams because that gets weird in and of itself. But thermal at absolute zero. This, you could use this as a way to generate electricity, almost, or just above. But thermal action makes this keep happening, and there is a voltage potential across this. In silicon, it's about 0.7 volts. In germanium, it's about 0.3 volts, which is why when you use a rectifier diode, it's got a 0.7 volt drop on it. They're usually silicon diodes. If you use some of the Schottky diode, fast-acting Schottky diodes, they're germanium. It's got a 0.3 volt drop on it. So what happens here is, if I have there's what's called an activation energy. And for silicon, I think it's between 1.2 and 2 point something giga electron volts, which is just a way of stating energy. And if you can put that energy into this piece of silicon, there is a chance that you can excite an electron to pop up into the conduction band and create an electron hole pair. So if you look at the old Bohr model of the atom, right, you've got a nucleus here, and then you've got some electrons running around in orbits. I think it's 2, and then 4, right? And so the way to think about this is energy comes in. Let's not use that E. Let's use an epsilon. That energy is absorbed, and it causes this electron to pop out, and now you have a hole. Happens all the time. Light comes out. It turns out that light in the band of sun on the low frequency end of ultraviolet all the way out, which is 300 or so nanometers wavelength, all the way out to near infrared around 1.1, 1.2 micron wavelength is enough to make that happen. In silicon, it's a 1-for-1. You get one in, you get one out. So constantly we're being bombarded by light here. Anything that's silicon, even in our bodies and whatever, electron hole pairs are happening. This is ionizing radiation. That's why we get sunburns. It's what leads to cancer, because the ionizing radiation causes this to happen and damages a cell, because this happens in a DNA and causes a DNA strand to break. Skin cancer happens. Turns out it's a useful effect in photoelectrics. They figured out a long time ago now in the case of your diode, if the energy comes in here and creates an electron hole pair, we usually say EHP, but I'm going to draw them. There's an electron and there's a hole. Well, there's a diffusion lifetime based on temperature and everything else, and because that diffusion lifetime is relatively short, they usually just fall right back into each other. There's also the diffusion length is based on the diffusion lifetime. They can't get very far. He'll go and want to pop in and want to pop out, and everything's happening. It just recombines and you don't notice it. The thermal energy that's causing this to happen is what causes this. Because there's a field here, an electric field between this N-type and this P-type, there's a bunch more electrons over here, and there's a bunch more holes over here. That draws a hole this way and an electron that way. So, if I get an electron, if I get a gamma ray, light, whatever happened here, I get an EHP, and it recombines. But if it happens here, if it happens anywhere in that diffusion region, now a hole is swept one way, and an electron is swept the other way. Now eventually, those are going to recombine, but they're going to first come all the way over here and create a difference in potential, and then eventually they'll work their way back and find a place to recombine. That's how a solar cell works. So we'll start off with a solar cell. If I've got this little thing like this, it's not going to do a lot of energy, but now I make, your standard solar cell on your roof is made up of pieces that are about, not quite that big. And this is a piece of, if you lay this on its edge here, this is a piece of P-type silicon, usually. It has an N-type deposition on it. So it's a giant freaking diode. It's this big around. And energy that comes in and lands in the diffusion region here gets swept both ways. So you can model this as a diode with some resistance some capacitance that's actually based on this diffusion zone. And if you've got a load somewhere to take so that charge, it gets swept across the gap, right? If it lands in that gap, now an electron will run this way and come back around to this side, and vice versa. And as long as the voltage doesn't go above that voltage differential gap there, so 0.7 volts for the silicon ones, it'll keep going current this way. If you put enough light on it that it goes above 0.7 volts, it'll actually forward bias and short itself out until it gets back down to 0.7 volts, which keeps it puts in. So that junction will never put out more than 0.7 volts or thereabouts. And then on your solar cell on your roof, there's I think there's either like 45 or 50 of them put in series, and I think it generates about 40, like 35 or 40 volts comes off, but there's a whole bunch of them. And each one can do about 5 amps worth of current. It's a series parallel mix, so they can get about 5 amps, I think, or 10 amps, depending on the cell. So now we go a step further. Somebody says, well, this is useful. If I can take a diode, and let's do this, and take an output off of it. So remember we talked about transistors and using a collector, a resistor and a collector path to be a load. So if we call this our load, and I have light coming in, this is an LED will do this, any diode will do this. LEDs are tuned to a specific color, and it's the reverse action, but they'll be especially sensitive to the color that they emit, generally speaking. Light comes in, electron-hole pairs happen, and it causes current flow through it. P side becomes relatively positive, so if you have, say, a 5-volt rail up here, now I've got current flow coming through, and now I get a load drop there. This guy looks effectively infinite because he's not conducting much current. He looks like a current source. He looks like probably 100 k ohms resistor sitting there. And so if I make this, say, 5 or 10 k ohm resistor, I'm going to see a voltage change here. Hey, once I figured that out, now I can put a lens in front of this and focus light on it. And now I've got a big area, focusing a lot of light into a small area, and I can get a big change in current for a relatively small change in ambient light. So, hey, that's useful. I can do all sorts of fun things with that. I can shine a light off of something, and if I've got a fast enough counter or an oscilloscope, I can see how wide that pulse is, and I'm basically doing the radar equation with a light beam now. I can see how far away things are. If I take 2 of these diodes side by side so that my light pattern falls like this, now I can tell a light thing from a dark thing side by side. Now we're on the first stages of an imager, right? If I put 4 of them on here with all these resistors and everything else, now I can do quadrants. I can say it's light there and dark there and dark there and light there. That's enough to get a lot of information. We're building our first imagers. So the very first imagers were actually just diodes out, biased up. And they're like, wow, this is neat. And I've seen some things where they've done, I don't know, maybe 10 by 10 little diodes, where people way back in the days of, Fairchild Semiconductor being relatively new. But it wasn't useful. I mean, it is, but the amount of effort you had to put into it to get it to be working made this one little thing really, really expensive.
4x4 got a lot of traction.
There was some really clever things that I've seen that were, they do rows. If you looked at the original, oh God, it was crazy. The original forward-looking infrareds, if you looked at it from the top, there was a scan mirror that went this way, and there was an infrared lens here that focused the beam here on an infrared diode, and that had a driver circuit that went around over here to I want to say it was an electron gun, but it might not have been. They played games with, some of them had actually an LED there that lit through, and this mirror's doing this, so it was doing a persistence of vision type thing. So as this mirror would scan across the image, it would repaint the image on the backside of the mirror, if that makes sense. And I think some of them had like an electron gun that ricocheted off them, had a phosphor screen, and then they got smarter and smarter and smarter as they went on. And if you tilted it this way and looked at, the mirror is running like this with an axis there, and there was like, 20 or 30 photodiodes running along there, the detectors. Now you understand why fluids were so expensive back then. There's a lot of clockwork stuff in there. So then in the late 50s, early 60s, I think it was, 1960s, RCA, I think it was. There's a couple of RCA, Westinghouse, a couple of different houses figured out. So at the time, the big, I don't know if you've seen them in all the movies and whatever, the big television cameras, studio cameras that they used, those used what's called a Vidicon tube in it, which is a lot like a CRT, where you scan an electron beam back and forth across, but they're doing the reverse. So as they scan the beam across, off over here sort of a ground, and they're measuring the current that's coming back off. You say, oh, okay, nothing. You know where this is in time as you're scanning the beam. Well, if there's light falling on it from the outside, this phosphor gets excited, and now when the beam comes across there, it recharges that, and you get a dip in your current over here, and you know, oh, that was a dark spot there, and you know how dark it was by how much current it was. Everything's this precision timing thing. So Vidicon tubes, ways to detect light, but they said this is crazy because these things were, the Vidicon tube was no kidding. The smallest one I've ever seen is about that long, about that big around. Actually, I think I've seen ones about that big, but those were very special, very expensive ones used for very special things. They came up with the idea of a charge-coupled device. A charge-coupled device can be a lot of things. A double EEPROM, or an EEPROM, is a charge-coupled device. And when you talk about a charge-coupled device, you're talking about storing information effectively in an electric field, just like you would in a capacitor. So it's charge that causes that electric field, and it's a coupling of the charge that you're using to transfer information. So if you imagine, let me look at this from the side, that I have a wafer like this, this is grotesquely thick, right? A real wafer is only, 2 or 3 millimeters thick. I grow on top a silicon dioxide layer, and then I lay down a metal plate. And this is P-doped, so this is a P+ substrate, and I've got it tied off to a reference somewhere that works. So this is all P+. So that means that this is majority hole carriers. I've got little holes all over the place, all through this. Now, if I put a large positive voltage on this, so I'll call it that, what happens is I've basically got a capacitor here. I've got this conductor, and I've got this poor conductor, and this much better conductor. But when I put this on, when I put this heavy voltage on here, when I put this, it sucks and basically pulling the electrons out and leaving a bunch of holes, and that creates a very intense.
I don't see a calendar selected for creating events. To select a calendar, go to the settings page in your Alexa app.
Thank you, Alexa. This creates a very intense electrostatic field in here, and it creates here what we call a potential well. This very, very high, I mean, this gap here is angstroms. I mean, you know, remember we talked about a million years ago, the capacitance of a capacitor is the plate size, the distance across them, and so the narrower that gap becomes, the more capacitance you get for a given unit area, and that's because of field strength in there. And the field strength gets huge in here. So the holes, because this is a positive here, are effectively driven out, but the truth is you get a whole bunch of holes in there. Any of the electrons that were there will get sucked in, but this was majority hole carriers, so there's very few electrons. But what I've done is I've created a diffusion region here. And this whole thing, if I have light come in and strike here, an electron hole pair forms, well, the hole is going to be immediately driven out. And the electron is going to be pulled up towards the surface and is going to stay there on the surface. So now, one photon comes in, one electron is created. Another photon comes in, another electron. I say created, it's broken loose. Now, I have electrons stored. And I can look at that. First of all, this is called a destructive readout because I have to basically empty that to find out how many electrons are in there. But I can look at it and say, oh, for every electron that was there, that was a photon, and you can do some math and come out and say there was this much energy, it was this bright, it was whatever. So now imagine, if you will, that I have gates set up like this. And I do this. And I wire them up this way. And I'm going to call this phase 1, phase 2, phase 3. And I'll make this a little wider on this side. So phase 1's high. I've got a well here, and I've got a well here. And I sit there and I let light fall on it. And I store charge for a certain, I integrate for a certain amount of time. I leave my shutter open. Then I close my shutter. And well, now I've got X electrons here and Y electrons here. And if you imagine that this is, if I flip it this way and this is two-dimensional, I can have a million of these, right? So I can have on the top of the chip, looking down, I can, right? So I've got this one lit and that one lit and that one and that one, so on. So now I have a 2D array of these things, and I can put a whole holy goblet of those on a fairly small piece of silicon. When they started out, they were like 50 microns on the side. You know, diode-sized stuff, but huge amounts. Now, I say, hey, you know what? I'm going to put, so this one's plus. I'm going to put charge on that one. And now this well is going to look kind of like that. And this one's going to look kind of like that. Because now I've got the electric field on both of them. And now my electron pile that was here kind of runs over, spills over. And now I relatively slowly take that down to a negative voltage. And this well slowly comes up and pushes those electrons over here. And now I've just moved my bucket of electrons from here to here, and simultaneously from here to here, and n times down the row from here to here. This is why it's called a bucket brigade device, which you're called that. And you can buy things called just delay lines that are based on bucket brigade technology. You're taking a sample of stuff and you hand it over to the next guy, and at the same time you take the one from the one next to you. So what happens here, I collapse this one, now I do it again. And they come out, right, and now I do it again, and I'm slowly pushing this charge out to the side. About the fastest one of these I've ever seen is on the order of, I've seen ones that claim 40 megahertz on some of the shift registers, but it's 20 and even 10 is more, 20, off the pixels themselves, 10 to 20, on a pure shift register, 20 to 40 is about as fast as I've seen. I've seen some that are a little faster. So if you look at this from the top, you got this going on. So I've got all these things that are moving this way. And then down here at the end, I'll put another one, and he'll be kind of funkily shaped. He'll do a number like this. So this guy will read into here, and then he will read into there, and then he will read into there. And so this is my, this is the one you'll call your shift register. So you'll do, everything will go step, 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 and they'll land here, and they'll time these phases the same way, so that this one here is open when it lands, and then they'll go step, 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 and you'll step all these out the end. So you'll take one column, or one row, depending on how they've done it. You'll shift it one column, and then you'll read out that whole column. And then you'll shift it another column, and then you'll read out that whole column. And this works really well because this matches the way VidCons work, right? You go across, and you come back. And you go across, and then you come back. And you go across, and then you come back. And so what's that doing? It's going across, and it's coming back. And it's going across, and coming back. What you got to do is orient it the right way, and it works exactly like a VidCon. Bang! The whole world started to go to CCDs at this point. Excuse me. You might want to go back. Sorry. All right. Now, what happens here in the side, so I'm just going to do the last couple. So we've got a couple of gates here. And what we'll do is we'll create a diffusion here. So this is a P plus, and this is a, this right. I think this is a P plus plus. Basically what you're doing is you're making a capacitor here. So now this P plus plus generates an electrostatic field there that's there all the time. And you'll come down and you'll tie to it. I'll draw you a schematic of what this is in a minute. And then off on another part of the chip, this will come up to a switch. It comes up to a VREF, a different one than the one that was down here. And then off over in here, you'll build an amplifier. So what I've done is I've used a reverse bias diode. Maybe that's an N diffusion. Maybe that's an N minus diffusion. like this. So if you remember the diffusion region in there, this looks like a capacitor. Very small, femtofarads. Femtofarads. Yeah, femtos. And we'll tie that off to a reset voltage to be reset. And there will be a transit, this is the transistor. So we send in a reset pulse. And then this drives an amplifier set. The way this amplifier usually works, it's usually only 2 or 3 transistors, and the output is usually an open emitter like that, so it's a current driver with some other voltage here, V out. And what you'll see is that, again, no, that wasn't right. That wasn't E++. If you put too much voltage on that, if you put too many electrons on that, it's going to forward bias and it's going to make your curve nonlinear. And so you'll never get more than about 0.7 volt out of this. This is like a unity amplifier usually. And then what you say is, however deep this well is, however many electrons it can hold, then you can figure out volts per electron, because this is never going to go above about 0.6 or 0.7 volts. And a really big well is maybe 150,000 electrons. So 0.7 divided by 150,000, and you're talking a couple of microvolts per electron. Which you got to imagine is way down your noise floor, which is one of the really nice things about a CCD device. Really low noise. Really, really, really low noise. Especially once they start figuring out what some of the problems were with them and doing things to fix those. So what happens here is I read this charge out, I dump this charge here. If you remember, V equals QC, if I remember right. Q is the charge, C is the capacitance, V is the voltage. It's Q over C. So C is really, really small. It's down to minus 15. So that means when I divide by it, it shoots way up. So even though I'm only putting maybe 50 electrons on there, and total charge isn't very much, I'm effectively amplifying it by the capacitance that's on it. But now I've got all this energy here, and I can't put the next one on. Well, crap, right? So I reset it, and I let all those electrons come running out of there, and then I open up my switch, and then I can put up the next one in there. And so I've destroyed, it's a destructive readout, I've destroyed the whole information as I read it out.
It's the clear mechanism on your sample and hold for transfer.
Yeah, yeah. So, and people at this time were starting to fiddle far around with putting diode arrays onto a single chip. And it was sort of a, I don't want to call it an arms race, but
Radicon.
if I look at, I showed you the top of this. This is very nearly 100% fill factor. I mean, a good set of CCDs, if you set it up right, you can be 99, 98% fill factor. That means 98% of my chip is integer. Now, to do the same thing with a CMOS, I have, each one of these is an effective diode, right? Negative, positive. I set up a diode, and I set up a reset, and then I have to have some way to store the charge. So I've got to build a capacitor here of some sort to store the charge. And now I need to put another switch here. Otherwise, when I reset this, I'm going to kill my charge. And then I've got to This is usually reset. And this is usually read. And then I've got to put an amplifier out here of some sort. And then I've got to put, if I've got a whole sea of these things out here, and I've got I've got a wire coming to do this, I've got a wire coming to do that. I've got to somehow bus all of these together. So usually I'll just use a transistor here like this to choose, and this will go to everybody in this column, and then they'll come out on another line, and I'll have a series of them down here. I'll choose which one I'll multiplex them and say which one I want to read.
And all that obscures your image area.
So yeah, so when we talked about it when I did mine, my thesis 20 some odd years ago, I made one of these. That there was some other stuff going on, and it was some analog processing. But what I came up with, I should have brought some pictures of it. I've still got paper. What you would do is you have, so light coming through, if it comes through where your transistor is, it's going to screw up your transistors. So you have to shield over the top of it. So you've got metal layers. So if I say that this is the area of my pixel, and what I found on mine was using a 2-micron process. I think my pixels were 50 microns on the side, if I remember right, about. And my diode was maybe that much of the area. And the diode was, in fact, the diode was actually less than that, because if you look at it from the top, what we would do is we would put in a deposition, and the diode actually kind of ran like this underneath, and then there was a tie here that brought it off to all that other circuitry. So the diffusion region was actually only this area around here. And that's not even a 25% fill factor. It was a very low, the fill factor was very low. Now if you think about that, I've got a lens coming down on this, focusing on this image plane here, and my pixels are here like this, but I'm only really getting maybe that much of them. I'm wasting a lot of energy. Problem number one. Now you can get around this. There's ways to get around this. They've always used these for infrared detectors. Once they got to the point where they made what we call a ROIC. It's a readout IC. If you look at it from the side, sure, it's only got this little spot, but what they do is they put a bump bond on there. And then they put a big thing like this on top of it. And that is an expensive process, because you have to align these things, right? I've taken a piece of material here that is all these diodes, and now I don't have a diode. It's got a connector here for a ball bond to go onto.
Oh.
And now
So the thing underneath is all the electronics,
the
but
thing on top
is straight diode.
is straight, well, not a diode, it's made it, it's little regions of diode all over,
Yeah.
with isolation bars in between. So if you want to do something that, I know, we know really well how to process silicon and make chips out of it and readouts, but if I want to detect an array in, I don't know, 2.1 microns, that's gallium arsenide. So now I've got to have gallium arsenide diode array. Silicon won't detect that out there. It's outside of its band gap. So, all right, well, now I've got to put a chunk of gallium arsenide on there. And if, it's like putting down a ball,
A BGA with the worst pitch you can imagine.
Usually what you do on these is, one will be, they're not balls, they're actually lands, and they'll be aligned like this, so they can be off a certain amount and still get where you want to go. But it's real expensive, because before you can't go and put this on and then dice it. You have to dice all these pieces up. So now you're talking little pieces of silicon this big, but now you've got to come in with a piece of whatever the material is and bump bond it on.
And why would it stay?
Sometimes it didn't. you end up, what you would find is you'd have your imager, and maybe there'd be like a bubble in it right here.
Yeah.
Or,
so.
or if you're doing some of the the mercury cadmium telluride is a very popular one for mid-wave and long wave. Call it 3 or 4 microns out to 14 or 15 microns. You use usually this bump is indium. Indium melts at like 90 C. So if you're out on a hot sunny day and your cooling's not on, they can actually melt. There's all sorts of things that can go wrong. But when you're talking infrared, you're talking cooled anyway, because you're trying to detect things that are hot. So, but again, it's expensive. You want some kind of resolution, it gets really expensive, really fast, because you've got to play these tricks. Now, the problem with CCDs was, well, gee, I want to do this readout, but it takes so long, right? If I look at this array, I'm just going to look one direction of all these pixels, right, or the shift register. When I shift from here to here, it's a multiplicative effect.
Some degradation.
Right. So let's say this is 99% efficient, right? Woo, 99%. That seems like a really big number. That seems like really good, right?
Until you get to the other end of the line.
99. So now I've got 99%. 99% of 99 is 98%, and now you're at 96, I think, and then 93, and then 92, and then 80 some odd. I mean, just start multiplying by 0.99 each time, right?
Yeah.
And you rapidly come out the other end with
You wanted resolution.
and you've got it, but you've got no signal left. But it's weird then, because this one that only had to shift 1, right? He's really bright. So for a CCD, this is called charge transfer efficiency. Needs to be at least 5 nines. So it's 99.99999% efficient. You can have 8 there, depending on the size of the array. So now you get problems. We're going to go back and forth between.
So now you're into rejection noise and.
Well, we're going to go back and forth between goodness and badness on both of them, right? So this is a badness, but you know, as processes have gotten better and better and better, this is mostly a non-issue in a CCD process. Now understand that the CCD process is a different process than the CMOS process.
Yeah.
So if I want to build a CCD that's got all the readout electronics built into it, that's hard. In fact, I'm not sure there's very many that are still doing this at all. I know Kodak did some a little bit with some of theirs, just the basic stuff, but and the voltages on this are stupid.
Yeah. I worked with Redcon at some point.
These voltages range.
Never Fairchild, just Redcon.
You'll oftentimes this reference voltage on this will be like 10 volts, and the V high will be like 5 volts, and the V low will be minus 12. And then if you imagine, oh well, C equal QV, but remember AC current is equal to I C dV dt, and now I'm shifting 17 volts in 25 nanoseconds. Those are not milliseconds, nanoseconds. That's a really big number. If I look at the gates on some of these, I could be looking at C's approximately 2,000 picofarads. Those numbers come out to amps. Those come out to like 1.5, 2, 3 amps on each one. So now you not only got a power supply that can drive, if you RMS it out, it's like 1/4 of an amp with 1.5 and 2 amp spikes on it every.
Got a huge noise source as well.
It's a huge noise source. It's going to get into everything. You're swinging voltages back and forth at high stresses. There's stupid, weird voltages that CMOS doesn't like, right? Minus 12 volts, you're back to BJT processes a lot of times. You got to do level shifters to get from what your computer uses, which is like, these days, it's like 0.3 volt, hell, some of them it's 1.8 volts. coming off, right? And so you've got a level shift 1.8 to 0 to 5 to minus 12. There's CCD is if you want a good image and you want to make the most use of your space and you are a scientist and you can afford it, you're going to buy a CCD, you're not going to buy a CMOS probably, if you're looking in the visible range. All these big telescopes, if you remember the KTMN, Korean no, you didn't see that one. There was a talk I arranged for IEEE last year, November-ish. Korea Microlensing Telescope Network, KMTN. 3 ground-based telescopes on the equator so they can look at, and they're looking for exoplanets based on gravitational lensing of a planet moving in front of something else. Those are CCDs, and their CCDs are 4 plates. The whole CCD array is that big, and they're on like 20 micron pitch.
Somebody who got some deep pockets.
The instrument were $10 million each. That's not bad. That's if you ask me, that's pretty good.
That's pretty good.
That's pretty good, especially considering what it was. I think they made 4 of them, one's a spare. So the image quality of a CCD is amazing if you have a good CCD. Problem is, they're a pain in the ass to use. Now, what you would see in cameras, there was video cameras and whatever else up until, CMOS was starting to come into play in the late 90s, I guess. And we're starting to talk about, we're going to do CMOS camera and whatever. What you would do is you would have 3 sensors, kind of like this, and you have a prism in front of them. Like this would be a red, this would be a low-pass red, and this would be a low-pass green, and then everything else would go through. And then you'd have an infrared shield on this end to knock out the infrared. So now you got red, green, and blue. And that's how you break them up. Or if you just had the one, then it was black and white. Or they play a game with a color wheel that would spin in front of it. And one of the downsides of the CCDs was, if you remember the old, like Toshiba video cameras and the VHS video cams when they first came out, 20, 30 years ago, everything looked kind of orange. You remember that?
Yeah.
The pictures of them looked kind of red. They had a red tint to them. And what that was you got your CCD here, these gates are polysilicon, which is a form of, you grow it on top of the silicon dioxide. It preferentially passes red. So your red CCD, if you had a red, green, blue, your red CCD always gave you a better signal than the rest of them did. And so everything's tended towards red. And then they figured that out and calibrated, did some calibration stuff to knock that signal down. So now, looking at CCDs, well, if I'm doing scientific stuff and I'm looking in red band, that's great, but that kind of sucks everywhere else, especially if I'm uncalibrated, right? Because I want to know that when I got 10 electrons in that well, I really got 10 electrons in that well, right? I didn't get 23 and because they were a different color than what I was expecting. So, there's 2 things you can do. One is they went to, instead of polysilicon, they went to a special indium tin oxide. And indium tin oxide is pretty transparent across the visible band. As long as it's not too thick. Remember, this is nanometers thick. That's one thing they did. The other thing you can do is you can do backfitting.
Yeah, what was the advantage of coming in from the rear?
Well, so there's a couple of them. So first off, here is where I sliced. I took a saw and I cut that silicon slug into a wafer, right? And so if I've got the silicon, this is monocrystalline. It is a single crystal. It's not like martensite steel or whatever, when you heat up, and it gets all these different crystal grains that grow together. They take great pains to make that one crystal. That whole great big slug, when you see the pictures of them pull a silicon ingot out, it is one crystal. It has no crystal boundaries in it. It is, seriously, it is one crystal. Now when I cut that crystal, if I look down at the crystal structure layer, and I don't remember what silicon is, but if I think about this, they're basically hydrogen bonds, right? I've got, the crystal lattice has grown, and I've got a hydrogen bond here, 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 this way, where these guys are all sharing electrons, right? What I've done is I've basically cut right there. So now I have, maybe I should have cut it this way, so it makes a little more sense. Next to one there. I have a defect in my crystal lattice. I've cut it here. Now I've come back and I've grown silicon dioxide on top of it. So here's a silicon with an O2. And here's a silicon, non-sulfur silicon with an O2 on it. And here's a silicon. And however they have to stack, but every now and then I'm going to get some sort of crazy thing like this. Because this is way off scale and stupid. And what I've got here is an electron trap. That wants an electron. That wants to share an electron. Damn it, that's how the whole crystal structure forms, right? Is by sharing electrons. And I've taken the electron away, and there's this hydrogen bond just hanging out there that says, I want an electron. Please give me an electron. Most houses don't have the capability to do a hydrogen passivation. One of the houses I worked with could. They would push hydrogen gas in and cook it in, and wherever these were, you get a hydrogen bond there. And that one electron, he would share, and he would be perfectly happy. But now, when you do that, you're creating a stress in the crystal structure, and you're doing some other things too that can cause some weirdness. If you don't do that, if you don't do some sort of passivation, what happens is, as I shift from bucket to bucket to bucket, occasionally I'll leave an electron behind, because it'll stick there. But eventually he'll release. And then he'll free up, and then eventually maybe another one will stick. And what you'll get is in your array, let's say we're reading out this way, and this is the shift register here, into our amplifier. So this stuff shifts this way, and then I shift that way. What you'll see is called a streak. So this one will trap an electron for a little bit, and then sometime later he'll release it, and you'll get false readings. You'll say, oh, that electron happened here, but no, really it happened over there. There's no way to know. And you can do a bunch of statistics on the stuff, and you can realize that, over 5,000 pictures that are just a plain white field, you can say, oh, it looks like I've got an electron trap there, or a couple of them, and there's a propensity for them to happen, but you still don't know, because it's a statistical process. And given any one image to the next, you don't know which one's lost that. There's image processing things you can do to help get rid of it, but it's an issue. So what they did was, there's, again, two ways to do this. You got your P plus here, and as you drove the holes out, they did what's called a buried channel here, where it was like really heavily doped, like P+++ maybe. And that creates another field underneath that even though you've got this really strong field here, you've got another field here, and that pulls the electrons down a little bit, so they're not running on the surface. So you're much less likely to hit a trap. Once you've done that, well, you've still got the issues of this blocking light. If you want to get really fancy, really good, you will then come back and cut this off all the way down to that P++, and then you'll mount them upside down. And now it's backside illuminated. But then you have to play games because the shift register is now exposed to light from the backside, so now you have to put down something on the backside to mask it so that it's not acting like a bunch of pixels too.
Yeah.
And generally what you'll do is you'll have a section off over here and a section off over here that are dark. So I can shift along this whole line and I should get black, 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 data, black, 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 black. What these ones tell me is my charge transfer efficiency, how well I'm shifting through. What these ones tell me is dark noise. Tell me about dark noise, because remember we talked about thermally generated stuff. So if I've done some amount of integration time, I can look at this and say, oh, I'm getting this many electrons per second noise. And that's a statistical process, but I can kind of lay it across the whole thing and say, I expected to be this many electrons of noise. A CCD at room temperature, and that might be a lie. If you take a CCD and you bring it down to about freezing, 32 degrees Fahrenheit, it's an amazingly clean device. It does not have to be super cold to be zero noise for all intents and purposes. We're talking statistically like one, maybe a half electrons with a noise statistically. You can't get a half electron. So those are some of the games you play with the CCD. I mean, you say, well, I got to do all this, and that's slow because moving this thing over here is slow because I'm moving through these huge, these are. I think the everything I've seen, things seem to come down about 8 to 15 microns. It's like a sweet spot in the size of pixels. You see sometimes a little smaller and sometimes a little bigger, whatever, but it's all designed with the optical train and everything else in mind. Because when you go smaller and smaller, you lose well capacity and a bunch of other things. But 6 to 15 micron pixels, if you're talking visible, 8 to 12 are what I used to see a lot of. And that stayed fairly constant over long, like over 10, 15 years of time. So that's a sweet spot. So what they said was, well, geez, this stinks. We want to be able to read these things out faster, right? Because, if this is a little thing, yeah, I can read it out at 30 frames a second. But CCDs get hard, especially if they get very big. Getting 30 frames a second can be really hard. In fact, for the Vidicons were, I think they did full resolution at about 30 frames per second. Were they 30 or 15? They were 15 frames per second. The CCDs were half the resolution, and they could still only get about 30 hertz. And what they would do is they would shift back and forth. They would basically shift the image area electronically back and forth, and to fill in the back interleave scans, so that they could get the frame rate up to what they needed to, and still keep the resolution. So what they started doing was, they said, well, geez, we have people who are wanting. Lucasfilm is wanting to do these high-speed, spectacular things at 60 frames per second imagery, at HD, at 4K by whatever, however many K it was. When I started making CCDs that could do that, because damn it, it's Lucasfilm, we want the best imager that's out there. Okay. And so what they started doing was a deal, it's called an interline transfer device. And so if you look at it from the side, you've got a diode formed here that was I think it was a P, yeah, it was a P plus plus. And then you had this setup. So this guy was always open to light. I'd open my shutter, I'd let the light in. I didn't even have to. See, with the full frame imager, if light's still on it, I'm still absorbing light while I'm shifting things out, so I have to close the shutter.
Mm-hmm.
So I'm still limited to mechanical speeds. Now I come here, and I put a field here, and I put a field here. All these electrons run over here, and I close this one off. And now this thing's already integrated in the next frame.
Mm-hmm. And the collection area is blocked.
I have a smaller collection area, but now I can read out and integrate at the same time. So I can take, as soon as I say, take that picture, I'm already taking the next one while I'm reading this one out.
Mm-hmm.
So there's no gaps between frames. Really fancy little thing you can do there. But now what you've done is you've said, oh, okay, I've got a row of pixels now that looks like this, right? And I have this funky little register here that pushes them off to there. And usually there'll be a whole column of these running down. And then we play the same game that we did before with another shift register here. So here you have your vertical shift register, and here you have your horizontal shift register. And now what have you done? And you've still got your guards. You've gone from the magical, 99-ish% infill factor. You've knocked yourself down to maybe 95 or 90. I've seen 80, maybe 80. Now it's still better than the CMOS. So you're getting better image quality. Now you can read out fast. You can see, I've seen these up around 100 frames, 120 frames per second.
Your aspect is also maybe weird.
Yeah, but you can, if you've got, actually it's not that bad, because if you, for aspect ratio, if you just assume that that's the center of this is the center of each one, they're on a regular pattern. So, you're not really affecting your aspect ratio. All you're really affecting is the amount of light that you're getting in. You're killing some of your light gathering capability.
But horizontal versus vertical.
Oh yeah, there are those. But the interesting thing is here, right? If I want to go really, really freaking fast, I can do my shift here and shift down, and now I can have another one in. And if I do this correctly, I can actually maybe have 2 or 3 frames shifting out at the same time. I can have 2 or 3 images rolling through this. One of the other games they do is they'll take a register here, they'll have the CCD here, and this will be all metal over, so no light will hit it. And they'll take this and they'll shift it out really fast there. And then go back and do the imaging on this one, because when you shift it out, you clear it, right? It empties it out. So they'll empty it all into this one, and then they can sit here and leisurely read this one out, while this one's still integrating. So it's not quite exactly frame to frame to frame, but it's pretty close. So, CMOS. CMOS has all the same problems. Electron traps, whatever. It's nice because I can use a CMOS process. CMOS process is what I use to make my CPUs. It's what I use to make practically everything in the world these days. So, looking at it from the top, well, a couple of things. If I look at the structure of it before, I have a diode to the switch, which is really a FET. I have another switch, which is really a FET. So this is sample, this is reset. And I have another capacitor here, which is probably done as a diode. It might maybe done as a diode, or it may be done as a two pieces of metal, depending on how they did it. And then I have another one here, with row select, and this all feeds out, and this is repeated, right? So there's another one of these. So I've got power coming in, reset. The reset, I've got power, I've got the actual reset pulse, I've got sample coming in, and what's row select? Row select might come up the top to make everything easy. And then I've got ground everywhere. And now I've got this thing again. So here I've got V reset, and I've got this switch onto this diode, into that switch, tied together into this capacitor, whether it's a diode or a capacitor, into this row select, and they tie up. And then down at the bottom, there's a big multiplexer that you say, this one, 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 this one. So now you start to see some interesting things that happen. The first is, we talked about before, you've got very small fill factor. Second thing is, every one of these is a noise source in your signal chain. There's some resistance here, there's some resistance in the wires, any thermal noise. CMOS is inherently, traditionally, CMOS is inherently noisier than CCD. If you want to take a good picture, you use a CCD because it's low noise. But I don't have, there are a couple things I can do depending on what I want to do, right? I can, when I transfer this charge over here, I didn't destroy it. I can read it out multiple times if I want to. Maybe there's a good reason to do that. So I actually, there should be an amplifier there, so another couple transistors maybe. If I lose my train of thought, it's fun. So I've got more noise, but I can do this more often. Oh, wait a minute. Moore's law has come along, and now we're doing 0.15 transistors, right? And rather than a 2 micron transistor. So that means now maybe this looks like this, and it's starting to challenge what a CCD was doing, area-wise, right? So now I'm getting a much larger collection area. And it means I have to change some stuff here for the electronics inside of it to be able to handle a larger charge and bigger voltages and whatever. But now my fill factor gets more and more and more and more, and I don't have to bump on a piece of silicon on top of it. As my processes are getting smaller and smaller and smaller, they're getting cleaner and cleaner and cleaner. So the intrinsic noise and hole traps and things like that cause weird effects, they're going away. Because I shift this straight out, I don't have the CTE problem going across the top. I don't need to worry about a process that's so clean that I'm going to get 5 nines of efficiency out of it. I can have a 99% efficiency out of it, and it's good enough. So they're ubiquitous, right? Every one of our cell phones now has a freaking, probably 2 cameras in it. One so you can do your selfie, and one so you can take a picture of someone else at the same time. And they're cheap because they're using a standard process and they're good enough. You know, you look at it and say, oh, that's a pretty good picture. There's a lot of signal processing going on there to make that thing look good. They also don't have the streaking problems. They don't have, they have a different blooming problem. So I didn't talk about blooming. On a CCD, I've got these little packets. So I say it can hold 150 electrons, right? And truth is, generally they hold 40 to 50,000 electrons. what happens is if you look at your signal output versus input,
It ain't straight.
it is very straight. It is a CCD is damned linear. Until you get up to about here, to about 95% filled, and then it does a change in slope. And then it flattens off at 100% or around 100%. And what's worse is when you hit that 100%, what's happening, the reason it's flattened off is because now these are going over the neighbors. So if you've got a really bright source on a CCD, you'll see what's called blooming. And you can see it on some of your cameras. If you turn down some of the signal processing and like point it, you'll see reflections on the water or whatever. Then you get this big ass streak like this. It's because they're blooming out into the neighbors and it's smearing out because there's so much charge there, it can't get rid of it. And you see it sometimes, especially on older cameras. The newer cameras, you don't see it so much. I still see it every now and then just because I know what to look for, right? Oh, hey, there it is. I know what's going on there. These don't have that. If you...
Because of the way they're read out?
Yeah, well, this is all isolated all the way around, so there's no... This is all basically grounded around here, so if there is enough to fill the tank...
So you're not handing it, it's not bucket ready.
Yeah, and so it will leak, but it'll basically go straight to the ground and go out. Now there's some other neat things you can do. And so a CCD is real neat because you can do a whole frame transfer, right? I can take all my wells, invert them, and turn them back, and reset the whole thing at once, and it's the equivalent of a shutter opening and closing. In fact, it's better than a shutter opening and closing because the shutter's not coming across my field of view like this. I just emptied it all out and said, let's take a picture. You will vary, personally I covet them. It's called a global reset for a CMOS device. If it's a global reset, every one of these reset lines is tied together. And you can go boop, and reset it all at once and start your image. The whole frame starts at once. Scientific CMOS does exist. They've gotten very good. I mean, like I said, they're not... Because the CCD sensor itself is so low noise, what sets your noise floor is your first amplifier coming out, just like for an RF signal chain. And so whatever noise figure isn't what's used, but it isn't the phrase that's used.
It's that one right there.
It's actually, your noise floor might be set by that switch, but that amplifier right there sets your noise floor. Now, he's warm, there's a million of them on here, this chip's running warmer, it's got more noise. If you cool them, I've read some papers where they talk about scientific grade CMOS sensors. I think they're usually looking out at infrared, not visible, but that are down around maybe 5 electron noise, 10 electron noise. Really good, really good. CCDs, I still look at those. Some of the stuff that we used to work with, we were calling, sub 5 electron noise. I mean, we were able to photon count. One of the other neat things, Texas Instruments came out with something. It's funny. Every silicon manufacturer gets into the imaging game at some point in time because they think, oh God, there's millions of them out there. We're going to make a lot of money off of this. And then they find out they're a pain in the ass and you got to do all this calibration, and they lose their ass and sell them off. So it's gone. Kodak got sold off to somebody else. Kodak was one of the big ones for years. They got sold off. They got sold again, sold again, sold again. Motorola had one. They cut theirs off, shipped it, and it's actually come all the way back around to Onsemi, which is the old Motorola now. So it's actually gone like from 10 companies, and I think it's come back to On, which used to be Motorola. TI got into them for a while. They were making all sorts of them. They still make the analog front ends and other stuff for them, but they don't make the CCDs themselves anymore, I don't think. Micron was making them for a while, but they sold that off to somebody else. It's just all over the place. I don't know where I was going with that. But what they do on these things is if you imagine a shift register here, and I'll take my row select and I'll bang it out this side, and I'll run my reset this way instead. So if I have a pixel and a pixel and a pixel, sorry, I gotta do this. If I put a shift register right here, this is a digital shift register. And I put another one right here. And I call this my reset register. And I call this my sample register. This is what you'll see more times than not. And then I'll have another register up here. It's my horizontal select. It goes to the multiplexer here. It lets me do a final readout to wherever it's going to go. This is what's called a rolling readout. You see these, they call it a rolling reset or a rolling readout. Imagine this is a lot more of these than there are. But my reset, I put my 1 here, and my sample, I put my 1 there. And now as it goes along, it resets. Now I can have the effect of I can change my integration time without, I can change my shutter speed effectively by moving these closer together or further apart. And basically I just have it loop right back around on itself, right? And so it just keeps feeding it through. And I say, no, I want to change my integration time. I want it to be a lot shorter, so I'll make that one a 1. So it's only a 1-line integration time. And so if I'm stepping them out 1,000 lines per second, well, that's a millisecond integration time. If I push it all the way to the other end, it's a 1-second integration time. Neat. Take your phone, take a picture, and do this. Or drive down the road and take a picture out of the guardrails. You might have to change it. Do it this way and do it that way. You get all your guardrails leaning one way like this. That's because I got this part of the image, and I got that part of the image, and I got that part of the image as the reset rolls along. Funny effects that happen because you're doing a rolling readout. If you're doing a rolling readout, you also can't calibrate your. It's not good for astrophotography type things where you're wanting to say, I want to stop and take a long image and see what's going on, because you don't know when that happened. It's hard to say which image is which. If you take this kind of a if you take a CCD camera and you point it at the TV, you'll see the scan line, right? You can watch the scan line roll because they're not in sync. If you take one of these and point it at the TV, you'll get these funny double bands where it's like all black, but there's an image going through because they're out of sync. You start getting weird, funky effects that this causes in one direction, but not another.
Orientations.
Well, yeah, and so it becomes a trade space, right? What do you want to do? These are the big major differences between a CCD and CMOS when you start hearing about it. If you're doing a digital single lens reflex, a lot of those are still CCDs. A lot of some of the point and shoot cameras are still CCDs. They can build the electronics fairly small and get you pretty good picture quality for the imager that's in it. Things have been slowly moving to CMOS because process technologies have been pushing CMOS to be better and better and better. For a good image, CCD is still the way to go, but you're going to pay more for it. One of the things that they did come up with for, and it's interesting, right? What you'll see now is a Bayer filter. So what is it? It's red, green, blue, red, green, blue, green, blue. I'm doing this wrong. Yeah, I think that's it. Red, green, red, green. Now I've got red. If I look there, I've got red, green, blue. If I look there, I've got red, green, blue. If I look there, I've got red, green, blue. If I look there, I've got red, green, blue. So now I can play a game where I can do like subframe sampling type things. This happens with CCDs also. I can come in and I can say, oh, I can dip basically, instead of saying this is a pixel and that's a pixel, I can dither back and forth and do some image processing and give a sharpened image. What you'll also see, almost every imager now, they have micro lenses on them. So we talked about, you know, this X% fill factor, right? I've only got this much of it being used. They've come up with processes where they've actually managed to put a lens on top that's only freaking 8 microns or whatever it is, but it focuses all the light down like this. And they figured out how to do that. It's a fairly easy process step. You do some interference patterns with your masks, and then you do an etch time, and so the mask is thinner in certain places than others. So a given etch gives you a periodic waveform that matches the interference pattern. So they make an interference pattern that looks like a whole bunch of lenses, and then the etch gives them lenses. And the silicon dioxide that they use is clear, so since you got a I don't know. That's probably 145% of all you ever needed to know.
Mm-hmm.
Is there anything you want to know?
2 questions. One, whole subset topic, probably more like the lens things. There's a whole area of camera tech that is fairly recent that has to do with depth of field changing, getting multiple magnification ratios all off of one camera system. That's one item. The other is, I had an event growing up that was, I remember quite vividly to this day, and it was the guys on the moon saying, oh, and isn't that a beautiful picture that we're seeing on our crappy ass camera right now?
I know the people who made those cameras.
And
Most of them are dead now.
there's the Earth, and there's the sun. What happened to the image? Ah, the image is gone. All right, what's the story on that one?
Those
What
were
type
Vidicons.
camera was
They were
it?
Vidicons.
They were Vidicons?
The live broadcasts were Vidicons.
And it zorched the...
It probably zorched the phosphor on the front end of it.
the coating on the whatever
Yeah.
it was.
It might have come back after a little while, but it's pretty easy to burn that stuff, especially. I actually know, I haven't seen them in at least 7 years, but I used to know the guys who made that camera. It used to be, if you go over, it's the National Electronics Museum now. It used to be the Historical Electronics Museum. In their space section, there was a technical Emmy there, and it was for the cameras that went to the moon. And they had the engineering model of the camera there, right, sitting there right with it. And that's actually, I was talking about some of those specialty Vidicons that were really small. That's what one of them was. Was that. So these guys were interesting. I wanted to talk about this real quick. There was one company for a while they came out and they sold a couple of cameras were made with them. I don't remember what the technology was called. It was like X3 or something like that. And what they did on their, I'm looking at this from the side, on their CMOS array, was they made a series of depletion regions like this. And I talked about this just a little bit, I think, at the beginning. Blue absorbs here, green absorbs here, red primarily absorbs down deep. Red makes it further in before it absorbs. So they did this, and they did a bunch of calibration tricks, and they were able to put a red, green, blue in the same pixel. And that was a big thing. We can give you a whole lot more resolution, and you don't have alignment problems between them because they're offset from each other. And yeah, but they weren't. I don't think it was a couple of years, but I don't think it went anywhere. I think it died. I think it wasn't worth the hassle. And one of the other things you can do is, so we're talking about CMOS, there's something called active CMOS arrays. And an active CMOS array, which is part of what my thesis was about a bunch of years ago, was you can do, because you've got processing capability there, you can do processing of each one of these elements, and you can base it on the neighboring elements. And what is it?
Some filtering and
Derivative of Gaussian and Laplacian of Gaussian, dogs and logs. Take that anywhere you want to go. You can play games where if you've got a bright pixel, it turns, you basically adjust the gain on the pixel based on all of its, a weighted average of all of its neighbors. So if you've got relatively dark pixels, they'll have high gain, but he's high, so those they'll invert and push it down. And so, like, if you take a picture with your camera of me sitting here with a light bulb, you're just going to get a light bulb and not much of me, right? Because I'm going to be all washed out. Some of the demos I saw of them doing this was you could see the coils in the tungsten film inside of them and see the guy just plain as day. And that made it out on the market for a year or two also, but I think also went nowhere because they finally came up with signal processing that could do most of what you need for it. Again, Moore's law drove processing to the point where playing special games in the analog domain wasn't necessary. Now, what was your question? It was
the weird focal depth stuff that's going on, or
there's
zooming.
There's a couple of different ways. Some of those that you see, they actually have like 6 different camera chips on them. And they're set up with different...
Is it really fancy lensing in front of the...
It's not fancy lensing so much as they're playing games with apertures. So whenever... I'm not an expert in cameras. I'm a sensor guy. I think they're neat. I think cameras are neat, but I don't really understand. So when you start talking about your f-stop and the speed of your lens, your f number is your speed, and you've got a camera system here, you've got a lens system here. It's doing things, and it's creating an image plane back here for the sensor to sit at. As you change the speed of this thing, you change the depth of field. And so, you know, professional photographers understand this. Oh, I want to get a big depth of field. I think the faster the f number, so like an f1, for instance, would
Make a pinhole camera.
which would have like
The best depth of field.
effectively infinite depth of field, which I guess that's a slow one, and a fast one, an f32, if such a thing exists, would, you know, everything here would be out of focus and everything out here would be out of focus, and there would be this really tight band here. So that lets you get that picture where you take the picture of the lady and everything around her is all soft and fuzzy, and it makes everything look all sweet. Makes Cruella de Vil look like a nice person, right? So what they're doing is, the ones I've seen, there's a bunch of different lenses. I read a paper, I didn't read the paper, I read the abstract of the paper in the last few months. They're saying they could do it with as few as 6, I think. And let them, and then a bunch of signal processing in the background and say, oh, I see that here, I see this here, I see that here, and they're all sort of co-core-sided. They can build an image often in 3D imaging space, in signal processing space, and recreate what it is. And then you basically get infinite. You can choose a depth of field and where you want the depth of field, because now you've built a 3D model in space, in memory space of what this thing is. It's one of the things they do. There's another thing called coded apertures. So a coded aperture is you play a game. I think we talked about this once before. If I've got a perfect lens and a perfect thing, what lands on the image plane is a sync function. And so you've got your primary blur circle, and you've got your first and second and third area discs as they go out. And the first area disc is like 99% of your light, your energy that's coming in. So now if you play a game and you look at it from the top, I'm drawing a lot of these today, haven't I? And so I say, my border circle's here, my first area disc is there. And over here, let's say I've got 4 pixels, or 3, maybe these 4 pixels, maybe this 5th pixel. And I've got that, and I get that secondary disc there. But I've got these like partially blacked, so I look at a point source and I calibrate this and I say, oh, well I see this much energy here and I see this much energy here. That starts to tell me things about what the position of this in this space, in this 2D space is. And if I want to, I'm basically making a little bit pinhole camera, a micron's pinhole camera right on the surface of my imagery. And I can start playing a game where it's called a coded aperture. I know the guy who invented this, and he's a great big proponent of them, because you don't need to put these expensive optical trains in, and they work for any frequency of light, and they throw away like 50 or 60% of the usable space. So they're interesting, but I don't know if they're ever going really.
Are both of those objects of the same instance?
If I put a point source way off in space, then I get, or a point source. If I put a bright light source way out in space, what I get here at this point is a flat field. And depending on my lens and focus, I can focus the one all the way down, or I can do a thing where it kind of focuses across everything and everything gets the same image. I can basically recollimate the light, and I can play games, and then I can start understanding the effects of what's going on the surface of my lens. And he came up with coded apertures. His name's Steve Gottesman, if you want to look up, if you're interested. He's the guy who wrote the patent on it, I think. No imaging system in front of it, no lenses, anything. You basically get infinite depth of field. You basically get great focus, but it's a huge signal processing problem on the back end, so you're doing all sorts of signal processing, and you're throwing away a huge amount of your imaging space. So you're also losing light. So,
I mean, Apple's decided to do, they've got 2 cameras, and they're doing all kinds of depth of field shit with that.
yeah, I don't know. I don't know. You're getting down in the signal processing realms and funny names of transforms. I can spell fast Fourier, I can spell Laplace, and I can spell Z. And if you gave me a week to go back in some of my old signal processing books, I might even be able to tell you what 2 of them are. But
At some point, I sort of got the impression that the dual cameras was for better autofocus.
it might be.
Just more information about the depth of field to focus on things
And
better.
that's actually, actually something I was going to get into in our next class is basically range. The next class I'm intending to be range detection. Different methods of detecting range and different sensors and a little bit about how they work.
Coded.
Coded aperture,
Okay.
I believe.
I started out for coated. That-
Coded,
that is-
C-O-D-E-D.
Got it, yeah.
Did you find it?
Yeah.
Yeah. So I remember him being all excited about it and showing it to me and me reading it and kind of understanding it. And I talked through it with him for a little bit. And it's like, that's what I'm saying. I look at it like, I get it, but it seems like you're throwing away an awful lot to gain very little. So maybe I'm wrong. Maybe they're using it somewhere and I don't know about it.
And your lens is not just a collimation, it's something different.
It's actually a pattern.
The pattern is there, but the lens, what you're doing with the light to throw it through the pattern is not just collimating.
That's the part that I'm not exactly clear of. It might be. Because when you look out at a certain distance, everything's collimated light, right? I mean,
Yeah.
and so there's dim spots and there's dark, bright spots, but when they come in and hit, it's basically interference effects and a few other things going on that let you figure out, oh, because this is this, and I'm seeing this much bleed over onto this pixel and that pixel. They're doing what do they call it, auto sharpening, where they do, you actually want the camera to have jitter on it, and you take a whole bunch of photos, and then you can start piecing them together, and you can do auto sharpening, I think is what they call it, and also called subpixel imaging, where they're playing the same game now. Now the signal processing's gotten so powerful that, again, you look at it and you say, oh, well, I see this bright spot over here, and I see these effects that are where things are bleeding over. They're doing some crazy stuff. I think they're also intentionally mismatching their optical training with their sensors, so that they're oversampling the optics. There's a sweet spot there, right? If I want to look at something and I want to see, if I want to look at a brick wall over here, and I want to be able to see individual bricks. Nyquist says I need to get 2 pixels on a brick, right? So I need to get 2 pixels in this direction and 2 pixels in that direction. So I need to get 4 pixels per brick. And probably I want to get 6 or 8 so I can see that line in between the 2 bricks and discern this brick from that brick.
Feature size versus.
Sure. Yeah, whatever my feature size is. You know, so if I've got regular bricks that are around 8 inches by 3 inches, but there's a half-inch gap in between each one, I want to be able to see the half-inch gap is different on each one. So that means I need to be able to see a half-inch size pixel. I don't have to or better. I don't have to Nyquist that half-inch pixel, right? I need to Nyquist the brick and the pixel together so I can discern the 2 apart. So now if I look at my sensor here in 1D, and I've got my lens here, I want that image, whatever that pixel size is, I'll optimize so that that lands right there. Right? So there's a line, there's a dark spot, there's a red spot, red spot, red spot, red spot, dark spot. Now if I'm off a skosh, I'll see a dim red, I'll see a little red, and a big red. And with my human eye, I'll be able to see that. So even though I'm not really Nyquisting that edge, I'll be able to discern it. Even in signal processing, I can see, oh, there's a dip there. So this is your optimizing, right? This is what they call if I remember right, it's Q equals 1. That means for each pixel out there, I have 1 pixel here. And I basically optimize now. If I do bigger pixels, I'm losing information. If I do smaller pixels,
You're oversampling.
I'm oversampling, and now I'm wasting money on this mirror, this camera system,
And your bandwidth.
and bandwidth. Yeah, there's all. So you get your optimum point is where it's a one-to-one match. Now you can intentionally oversample, and when you intentionally oversample, now I get 1 pixel out there lands here, and maybe I don't report back to the image, but this 1 big pixel. But now I can play signal processing games in here, and I can say, well, that edge, this pixel is darker than this pixel by 20%. So I know that that edge is a little bit further this way than it is that way. And now I can do subpixel imaging. And that's the same game you're playing if you mutate or cause jitter in the imager when it's moving around. You're stacking all these images together and you're seeing how things are moving from image to image to image, and you understand, oh, that's really there, and you can sharpen the image that way. Then they get people to get really fancy and they look at it, they can redesign the lens based on what they see in the thing because they've oversampled it so much, and they can play all sorts of fun games. Any other questions? It's 9 o'clock. Everybody bored? Just awful. I see lots of deep thought out there. This wasn't the normal class, this was just, what's the difference?
Well, those sensors are certainly in everything we touch.
Yeah.